Hello and welcome to today's webinar. My name is John Kowalski. I'm part of the marketing team here at BitGardener. I'd like to welcome you. Thanks for joining us today. Our speaker today, Mr. Andy Stumer, he is our managing director of our VMA Getzman or dispersion business. So he'll be presenting today on the pre-dispersion process. I also dropped in the chat a link. We are having the second half of this series on media milling next week. So I did throw in that registration link. If you're interested there, you'll also get emails that are scheduled to go out this Friday. We are also recording this, so immediately following the presentation, you will receive an automated link. Feel free to take a look at it down the road, share it with colleagues, take some screen grabs, whatever you need. And also note, if you think of a question after the fact, you can simply hit reply to any of the marketing messages you receive. It'll come to my team. We'll get that to Andy and his dispersion team or the right technical expert in your area. Today's presentation will run about 45-ish minutes. If we have time for questions, we will definitely get to them. If you have any questions, just drop them in the chat box and we'll get to them time permitting. If we do run out of time, Andy or someone on his team will follow up with you directly just to ensure that you get those questions answered. So Andy, you are fresh off vacation, yeah? Welcome.
That's right, John. Yes, fresh off the airplane. I actually just got back yesterday. So
wow, nice.
Yep.
Well, welcome. I'm sure you're raring to go, so it is all yours, sir.
All motivated and ready to go. So
there you go.
Thank you, John, for the introduction. Thank you, everybody, for joining us today for this great series here. I'm glad you could make it. And as John mentioned, this is actually the first part of the dispersion process, which is always two steps, right? You have your pre-dispersion, and then you have your fine dispersion or milling part, which we'll be doing at a later date. So John will send out the email and keep you guys posted on when it's going to take place. Okay, so we're going to start out with a quick introduction. Just talk a little bit about the company and the relationship that we have with VMA, the manufacturer of the Dispermats here at BIC. We're going to dive right into the dispersion process, and then we also have a section about lab as well as production equipment. We want to cover some QC capabilities and then talk a little bit about our fantastic laboratory in Wallingford, Connecticut at BIC USA, where you can actually come up and visit us and bring your material in and to do trials on our machines before kind of a trial before you buy kind of scenario. So VMA Getzman, well known in the industry as a manufacturer of really high quality dispersion machines. They were founded in the early 70s in the middle of Germany, about 30 miles east of Cologne, is where they're located in a small town called Reichshof. And the original, well, one of the previous CEOs for BIC, or BIC Chemie, as it was called, was good friends with Mr. Getzman. And he brought some of these Dispermat units over to the United States, to Wallingford, to our laboratory. And when we had customers come in, and that goes way back to the late 70s, and then people started seeing those Dispermats running, and they were like, wow, these are nice. We would like to buy them. And VMA at that time didn't have a reseller in North America. So BIC, started negotiating with Herman, and we basically came to an agreement in 1988 to have the exclusive distribution rights for the US and Canada. So we do everything from the sales part to servicing the machines right here in the US. The company is still family owned, so the two sons are running it. Christian and Martin Getzman, they split responsibilities. They have about 100 employees globally, and that also includes some of the service people and some of the agents that they have in various parts of the world. So they're pretty well represented all over. So if you have facilities in Asia or Singapore or anywhere else, they can really take care of you. The picture on the bottom shows you the very first Dispermat that was introduced back in 1973. And when I started with BIC about 20 years ago, one of my very first visits was with the customer, actually in West Virginia, and they called me one day and they wanted me to come in to replace those Dispermats that they had purchased. That they were exactly what you see on that picture right here. Well, when I went in there, I saw about 10 of these units running, and I'm thinking, why would they need to replace them? And it turned out that they thought that they were too old and they couldn't see the control panel, the information on the panel anymore because it was all scratched up. So what happened was they only had to replace the control panel, and they were then still functioning and running on the original Dispermats. The motors having been made in the early to mid 70s. So I believe they're still running today, and that just speaks for the quality of the Dispermat, the motor technology specifically, which are direct drive motors, and there are no belts or anything like that you need to replace. So they're really durable machines, and also, if you ever worked on a Dispermat, extremely quiet. Even at very high RPMs, you can really hardly hear them. So again, they are pretty global. Most countries of the world, they're available, and then 40% of all the machines that VMA builds is custom. So there are a lot of new end-use markets. Just think of like batteries or fuel cell, just to name a few, or 3D print. They all have different requirements, but VMA can actually make custom systems to accommodate these specific applications. Add nitrogen or any type of vacuum ports for on vacuum covers to use inert gas and have those connections, and they will be able to do all sorts of different accommodations. And they really have a complete solution for not only lab space, but also for pilot as well as production. And here in North America, we started production, offering production units about 5 years ago, and it's been a really good success story so far. So the customers that are using them stateside are very happy with the performance of these great machines. The laboratory, again, we have in Wallingford, Connecticut, and then there is one in Germany where you'll be able to come in for trials. So with that, let's just dive into the dispersion section. So what are these machines actually used for? So it all was derived really originally from the coatings industry. So that's why you're seeing a slide here for the different pigment classes, but obviously it's used for many other or new end-use markets. But so the different pigment classes that the dispersers are used for, we differentiate here organic or inorganic pigments, the functional pigments, and then we have obviously the metallic pigments, or special effect pigments, as they are also called. And the reason we are dispersing is to improve our gloss, transparency, color, our color strength, and then cleanliness of shade. But ideally, we want to also save money by reducing the particle size, allowing us to use less material, and then basically create more surface area, helping us to save money. So that's really what it boils down to. So we are dispersing to improve our wetting. The van der Waals forces, these invisible forces that are holding our pigment particles together, is what we want to break up with the shear force of the blade. And then we want to basically reduce them back to primary particle size, which we will then require some sort of a media mill with media to really break the binding forces even more, and then reduce these agglomerates down to the primary particle size. And that gives us, as I said, better color, better gloss, overall better appearance. Our pigment efficiency is improved dramatically just by going from 30 microns to 2 microns or 1 micron. You'll see a huge improvement. in your pigment efficiency. That translates straight to dollars, and you get also better product consistency from batch to batch, formulation improvements, and giving us also consistent particle size distribution. If you do a good job dispersing, will also help us get better results when we upscale from laboratory to pilot, as well as then all the way up to production scale equipment. What happens if we don't properly disperse our pigments? Obviously, the product isn't going to look as pretty. We're going to have issues maybe with color change, with stability of our pigments. Pigments flocculate together, that also is a formulation issue with the right additives that you need to select. Sagging, leveling, settling, and reduced gloss levels is another one, and separation, just to name a few issues that will arise if we don't properly disperse our material. So it's very critical that we have good stability. So that also means that, pigments require strong color fastness that will keep them more stable over time so they don't fade as fast. The brighter the color, the brighter the finished product, the better the color, usually. And then obviously pigment size, the smaller the pigment, that will give us better transparency, better color. And then again, it's a huge cost savings by reducing particle size and increasing our surface area. Viscosity is also critical. We want to be in the right window. Usually we want to be on the lower side. If we get too thick, it's very difficult to get the donut effect. And then also when we do media milling, to actually have the material flow through the milling chamber. And it's really critical that we have good flowability. And if it's not, if the viscosity is too low, that could also be a challenge in putting in enough energy to break up the binding forces. That means we have to disperse for longer periods of time. So try to aim between 1 to 5,000 centipoise, and that would be giving us really good viscosity range to process the material. But if you are higher, it's still okay. It just maybe requires some adjustments in terms of blade diameter and so on, as well as when we go lower, we also have to make some adjustments to make sure we can put in the right energy and we get a good dispersing effect. So important here is that we are not really trying to destroy particles, right? So we're not crushing them or anything like that. So we're really trying to break up the binding forces, these Van der Waals forces that are holding these particles together, and then turning these larger clusters, these agglomerates, and turning them into aggregates. And then finally, we want to bring them all the way down to the primary particle size, where that would be done through the milling cycle or milling process or fine grinding, which will be covered in the next section of this dispersion topic, or next series that we'll have in a few weeks. So it's really only the shear forces that are responsible for that separation. And then again, the right additives are required to keep these particles then in a suspended state so they flocculate back together. This slide kind of shows you the difference between the different pigment sizes. So I think it's kind of interesting, just giving you a quick look what that looks like under the microscope. And then this slide here, I like it a lot. It kind of really shows you in detail the different particle size clusters. So if you look on the bottom, you can see that those building blocks or these particles that look like the cubes, that's actually the large blocks here are the agglomerates. And then by using a cow's blade or the pre-dispersion process, we turn them to aggregates. And then when we want to go from the aggregate cluster down to primary particle size is when we do actually the media milling. So that's kind of showing you on the slide right here what these clusters look like. So starting out agglomerates, large clusters, use a blade. Pre-dispersion process, we want to be about between 10 to 30 microns of particle size. Then when we start the milling process, going from aggregates to primary particle size. This here kind of gives you a different view of the process. So we start out again with the blade, very important to wet all the particles and then do the deagglomeration and bringing the particles down to, again, 10 to 30 microns, kind of the threshold. And then when we get to that point, it's kind of the law of diminishing returns. We can keep on dispersing, but we're really not able to put enough shear force into our mill base to continually take these aggregates and bring them down to primary particle size. That's when we need to move over to a media mill. And that will help us get from these 10 to 30 micron particle size down to low micron range or even into the nano range, depending on the application. But it's critical that we use a bead mill, or some people use 3-roll mills, but that's what we offer is a bead mill with different types of mills. But we always use beads. So again, here you can kind of see 10 microns kind of the threshold when we stop using a dissolver. At the low end, usually it's between 10 to 30 microns, and then we start the milling process where we can actually go all the way down to below 50 nanometers. We have some application where that's required. Takes you a long time to get there, and you have to use really small media, but it's definitely possible to get to these small particle sizes. So the dispersion process in a nutshell, like I said earlier, always 2 steps. We get the first step, the pre-dispersion process. Critical tape speed window is 18 to 25 meters per second. We use a blade with our high-speed mixer or dissolver. We have different series of dispermats, SC, LC, CV, CNAE. We'll talk a little bit about the different selections we have. And then for fine dispersing, milling, and grinding, which is that second step, we take the aggregates down to primary particle size. We got to remember that the rotor speed is a lot slower than when we pre-disperse with the blade. We'd be looking at about 10 to 16 meters per second. For that, we use the bead mills, either vertical bead mills, a basket mill, which some people refer to as immersion mills, or horizontal bead mills, which probably a lot of you are pretty familiar with. So these are the options to get down to the really, really small primary particle size when we are grinding or milling. Okay, but back to pre-dispersing. So when we start out, we're going to have to fill our container depending on the volume that we want to do. So basically, we want to look at 2 things. We want to first look at the fill rate. We want to stay about at a 50% fill rate in our container. We don't want to go much over it. We have maybe a maximum of about 70%, but that's really the absolute maximum. Anything more than that, we're going to spill our material when we put in the energy. So we want to stay around 50% ideally. And if we don't have that much product, you can go down about to 40, but that's the lowest. You shouldn't be going much lower than that. It's going to give you issues with oscillation. So you really want to make sure that you have at least 50%, that's or 40%, but 50% is your sweet spot. The blade diameter should be about 1/3 of the diameter of your container or vessel. And that is the ideal ratio. So if you take a look at that table on the right side, it kind of shows you the different container sizes on the bottom, kind of going from 125 milliliters all the way up to 65 liters. And let's say I'm taking 1 liter, for example. So it's about a quart. You can see here that you can have a range of 30 millimeter blade all the way up to a 70 millimeter blade. So you're not fixed to one blade. But ideally, you want to start out with about 1/3 the diameter of the blade. So I would probably say would usually be about a 50 in this case. And then depending on where you are with your viscosity, you can either move up or down with blade diameter. So if your material is thinner, you want to reduce the diameter of your blade and basically make the diameter smaller. So that will give you better traction for low viscosity products. When you get really thick with your material, then you want to increase the blade diameter. And there'll be another slide. No, that's the calculation here of the tip speed. But you basically want to, depending on how your product is formulated, you can make these adjustments to the blade. So I always start out with about 1/3 diameter, and then you kind of see the movement inside of the container. If you're looking at a nice donut, then you know you have probably selected the right blade. If it's too thick, then you may want to increase the blade size. If it's smaller or if it's thinner, then you want to reduce the blade diameter. The critical calculation here for our tip speed. Remember, we said 18 to 25 meters per second is where we want to be at when we pre-disperse. So we got to be able to calculate that. So a lot of the dispersers that are available on the market don't show you that number. For whatever reason, you have to calculate that yourself. Our models, the new ones, all have that data on the screen, and so you don't have to do that calculation yourself. But it's basically the RPM of the blade of the shaft times pi and times the diameter of your dispersing blade. And if you want to calculate meters per second, then you're going to have to go with express the blade diameters in meter. So if you're using a 50 millimeter blade, that will be 0.05. And then you divide everything by 60. And that will give you the exact meters per second value based on the blade diameter and the RPM that you are currently running. And again, you want to be between 18 to 25 meters per second to optimize the dispersion window. So that's a very important formula. And then we have that infamous donut effect. And it's called that because it really looks like a donut when you optimize everything and you have selected the right dispersion blade and the right tip speed. And that's what you should be looking at, is a really beautiful donut forming while you're dispersing your material. So this is what's happening. So the blade actually has these teeth, right? These edges on the edge of the blade. These teeth are popping up on the bottom of the blade. So that's where actually all the shearing is happening. And that's what's causing the breaking up of these binding forces, and then optimized everything that will create that donut that you ideally want to see when you dial all the parameters into the process. So here you're running a tip speed of 21 meters per second. We're putting in 850 watts of energy. So this to me looks like everything is optimized. Looks good. We're going to run this for about 15 to 25, 30 minutes, and that should be done. You know, that product can then move over to a medium mill when you see something like that. You're going to have situations where you're going to also put in 21 meters per second, but you're only going to run at 320 watts of energy. So when you look at that picture, that tells me that there is obviously no donut. I'm not having any luck putting energy into my mill base. That means that viscosity is probably really low. That kind of shows it on the picture. It's kind of splattering around a little bit. Not a lot of energy going into my mill base. So I can probably increase here, my formulation and increase the viscosity of my material, or increase my milling time. That means I need more time to put the energy into my mill base to really break up these binding forces. Doesn't mean we're not dispersing. It just means it needs more time because we're only putting in 320 watts of energy, So the next slide here is the opposite. I'm having 21 meters per second. I'm putting in 900 watts of energy. I'm not seeing a donut at all. It's because probably my material is very thick and it's just not showing a donut. It's donut is not forming. It's similar to a very high viscous material, and it's just moving around. You're dispersing. You're just not seeing a donut because you're putting in 900 watts of energy, which is good, but you're not having any way there's no way that the donut can actually form because of the viscosity of your material. So that's what's happening right here. Okay, so important to remember is to get a really good dispersion result and have it perfect for the next step for milling is we want to be look at how long are we pre-dispersing. Again, 10 to 30 minutes. We want to ideally have a donut effect that should be visible. It's that visual cue. Again, tip speed 18 to 25 meters per second. We also want to look at the diameter of our dispersing blade. We want to use the right choice of impeller disc. There are different types on the market. Everybody has like their own preferred design. You want to make sure that you choose the correct one. 50% fill rate, ideal. The range 40 to 70%. We want to look at our pigment and filler concentration. Dispersing, if we dial in all the right parameters, we're putting in a lot of energy. You saw before 850 watts of energy is quite a lot of power, right? So what that means is we're going to heat up our mill base relatively quickly. So it's recommended that we also have double wall containers with jackets so that we can actually cool our mill base while we're dispersing. That's very important. When we're milling, it's absolutely critical because that's when we really put in even a lot more energy, and then it's an absolute must. Pre-dispersing, some people think they can get away without using double wall containers because they're only pre-dispersing sometimes only 10 minutes. It's okay. But if you pre-disperse for longer periods, like you go out to 30 minutes, I think it's highly recommended that you're definitely cooling your mill base, especially when you're running solvent-based products. Then it could become a safety issue. So always make sure that keep the temperature on the lower side and then use the correct additives again that will give you all these good properties that we talked about that we want to have when we are dispersing and when we are storing the material or moving it over to the bead mill. Okay, so the difference here in a nutshell, we need both, right? We need the dissolver and we need the bead mill. This slide only just outlines the differences between the two. So with the dissolver, it's the first step in the process. Because we are only using a blade, we're not using any beads. The amount of energy we're putting in is somewhat limited. That means we also have limited shear force. It's only there to deagglomerate. So we're going to take the larger agglomerates and we turn them to aggregates, but not to the primary particle size. It's very important that this is always the first step of any type of dispersion process. If you think you're going straight to a media mill without first pre-dispersing, you're probably going to end up with a clogged mill. You're going to have either, the screens clogging up. You're going to have all sorts of flow issues. So really important that you always pre-disperse first and then measure the particle size. And then when you're within 10 to 30 microns, that's when you should move over to the bead mill. And then obviously some people think, oh, I'm working with the dissolver. That's all I need to do. I can stay there. I don't need to mill. Well, but then you're going to have problems with the product quality, right? So we talked about that earlier. It's really important to get the best looking product and performing product. You really need to bring the particles down as low as possible, primary particle size ideally, and that will give you the best looking and best performing product. In the milling process, obviously we use speeds, we have a rotor, a lot more elements in play, allowing us to put in much more energy into a mill base, really now reducing the aggregates down to primary particle size. That will give us the best looking product, and also helping us save the most amount of money because we're increasing the surface area dramatically when we are milling. Okay, then we have the Dispermat, which is the dissolver that does the pre-dispersing, but you can also use the same machine, which is the beauty of a Dispermat, to do other things. So you can use it to disperse. You can use it to mill by attaching a basket mill on the same unit, and I'll show you that. But you can also use it as an emulsifier if you want to mix, two different liquids together at a very high shear rate, or you can use it as a homogenizer as well. So that's also possible, like a mixer, or as a propeller tool or a butterfly tool options there. This is a great picture, kind of showing you in the middle. You see a standard disperser. You're looking at a picture of a Dispermat AE with the cowls blade on it. So that is right now doing the first step in the dispersion process. It's dispersing. Now, if you want to go and use the same machine for fine grinding or milling, all you would have to do is purchase a TML on the bottom right, the basket mill, or an APS, which is a vertical bead mill. These are two optional, these are basically accessories that are parts that will fit onto our AE Dispermat. So you can actually very quickly go from one tool to another and make that machine work for many different applications. And by going and opening the clamping ring right below that motor flange, you can take that clamping ring off, turn that assembly like 90 degrees, you pull it out, and then you just pop in any of these other attachments like that basket mill. And now you're milling with the same machine, or the vertical bead mill, or a rotor stator, the SR, for homogenizing. Or you could also add a vacuum system, a CDS as it's called, also if you try to remove air bubbles. The ASC is a wall scraper system that's also an optional attachment that you can purchase to aid in removing any thick substances off container walls, scraping that clean and moving everything back to the middle of our container to make sure it's properly dispersed. So these are all optional attachments that you can buy when you need them and don't have to buy at the same time when you buy Dispermat. So we have an LC Dispermat, which is our low-cost option. I'm not going to go through all the features, but it's relatively economical. Doesn't do a whole lot except just spin the blade at very high speeds, up to 20,000. Doesn't give you temperature reading or anything like that, but it shows you the RPMs on the display, and it has a timer function. Pretty simple, easy to use. The newest member to our family is the new CV3 Evo. It was introduced last year. We just had it at the a battery show. We introduced it in Orlando and at the European Coating Show a couple of weeks ago. I was over there, and it's a really good-looking, very functional piece of equipment. There are two models. We have a basic and an advanced. The basic basically just has all the important information on the screen. The advanced allows you then to take all the data and that you are collecting during the dispersion process and then create a lab report, transfer it over to Excel. It'll come with an additional, with a scale that you can use to weigh out your raw materials right next to the Dispermat. And then you'll see the weights on the display. It's a beautiful display. It's got haptic buttons that are really solid. And then the whole face of it is glass, so it's very easy to clean. You don't have to worry about somebody destroying a foil or anything. For chemical resistance, it's glass, so it's good quality product. There's also all these different attachments that are available also for this unit. So you can buy a basket mill, you could buy a APS speed mill, a vacuum system. Uh, so the rotor stator is also an option. So it's very versatile piece of equipment. Again, 20,000 RPM maximum range and extremely quiet. We had it turned up all the way, and people were like, wow, can't even believe this machine is actually turned on. That's how quiet it was. Then we have a CN model. There's going to be a facelift to that this year. It's going to have the similar display to what we have on the CV line. So it's going to also be updated, giving you the tip speed now, all the critical data points that you'll be able to see on the CN. And then the CN also allows you to upscale, staying within the same model series all the way to a pilot unit. So that makes that very attractive. If somebody says, hey, I'm trying to develop a formula in the lab, but I want to be able to replicate it in a pilot unit, you can do that with the CN and then actually go from there all the way up to a large scale production unit. That's possible with the CN. And then we have, of course, the AE. Right here also, you can already see it with that facelift already that was introduced last year. Here we're showing you the AE with the basket mill attachment on it, not a cowl's blade, just to give you an idea what that would look like. And it's got a C controller, so that basically gives you all these options on storing data. You can program cutoff values if you have, let's say, a product that is sensitive to, it has a certain temperature range you don't want to exceed, then you can basically lock that in, and it would then, once it reaches that point, either shut the machine off or run with a different energy input or different speed. So there are a lot of different options that you get with that C controller that you might need when you want to go and upscale or just for R&D purposes to collect the data, look at lab reports and trends and all that. So that's what you would want to have in the lab, especially if you're trying to formulate and make something that would work in production. So that gives you all these important values that you would need for that. And then we obviously have the same logic here. We want to give you a lab unit that you can then upscale to pilot, and it would function exactly the same way. And then from there on, you can also upscale to production if that's something that you are interested in. So here we have the Dispersion SC, which is our production scale unit. We can go all the way up to 2,000 liters of product. Excellent tool to also mill, because we have that quick change system. What we have on our smaller units, we also offer that on our large units. So that makes that machine extremely versatile and a cost saver, because you don't need multiple pieces of equipment. You can buy one machine to do both your dispersing and your milling. We also have a vacuum option. Some people, like I said earlier, they want to remove all the air. The air bubbles can be a hindrance or are a hindrance to an optimized dispersion process. We have a removable cover for easy cleaning, easy access. There is the ability to purchase a wall scraper, even for the production unit, that has its own motor to ensure that the container walls are always perfectly clean. And then again, I think I mentioned that on our lab units, but we have explosion-proof models, and we also have that for our large production scale models as well. That's an example here of a vacuum machine for production scale. I think that's a 350 liter container, so we can have much larger vessels under that machine than what you're seeing right there. But the beauty of using vacuum is a number of things. So allowing us to put energy in more efficiently by removing these air bubbles. They're almost like tiny little air mattresses. And think of it this way: it's like if you're wearing a life vest, and somebody put on a boxing glove and were to hit you, that that wouldn't hurt that much because you're wearing that life vest. But by removing that life vest, now if you get hit, that impact is going to hurt, right? So that's kind of the same idea when we're dispersing and milling. These air bubbles, they act like air mattresses, or like that safety vest. So take that out, and then you're going to put in more energy. It's going to be more efficient, and that will allow us faster milling times. By removing the air, we'll be able to get rid of the foam and then have faster product transfer, from one vessel to another, like a storage tank, if that's something that you want to do. There's also the option of getting different purging valves for nitrogen or argon or any other inert gas. So that's also a possibility. Some people like to create a nitrogen blanket. So we can do that with that system also. Okay, then we have just some quick overview over the different control panels. So here on the left, you see our C controller, which is that what you have on the AE units. On the CV units, it's very similar, as well as on the new CN. So you get all the important data points on the screen, like your RPM, your energy input in watts, your torque value in Newton meters. It's an indirect measurement of your viscosity, so we can measure that. We can also give you that tip speed, so you don't have to calculate that yourself anymore. The temperature readout, and the timer function. On the right, you see a very standard crude control panel for a production scale unit, right? So a lot of people prefer to keep it simple in the production environment, not a whole lot of finesse needed to operate the machine. It's more of a crude environment, so you don't want the smaller buttons. So this is actually the ideal shape or design for a production scale disperser. We also have the option of having a programmable panel, PLC unit made by Siemens. That gives you the option of integrating all your flow process into or the machine into your flow process. So that gives you the ability to program, like, for example, a load cell into that unit, and then you'll see all the data right there on the screen. So you have a lot of different ways of how you configure it, and that beautiful PLC panel made by Siemens. That's an old slide. We're going to actually take that out the next time. These are just showing you kind of like on the older version what that looked like when you programmed the cutoff values for your temperature limit, as well as like you setting up some parameters for a different for a product. You can give it a name. It's a lot more attractive now with the new GUI, so that it looks different. We just have to redo that slide, and basically the idea stays the same. It's going to be able to either you modify your RPM or your energy input depending on how you run the machine, either with constant power or constant speed, and then you can basically set it up for a particular product. And then next time when you're running the same product, you're just going to recall, let's say, blue 1, and then it's going to use all the exact same parameters. So you're going to be able to replicate the process every time when you're running that material. Then we have trend lines showing you live how the dispersion process is progressing, and that also looks very attractive on the new control panel. We can do a net power calibration. That means on our AE unit and the new CN and CV as well, allowing you basically to set the machines to an absolute 0 point. So meaning even if you're turning it on and running it without product, the machine would already use energy because it has to rotate the shaft. And then some people want to have a really 0 point when they look at the energy input and torque values. So they're going to do a net power calibration. So that's what is possible with the Dispermat. And then that's the Windows 7 software, just basically uh, showing you the software that was available. It's actually been discontinued now, but the new machines will all send the data straight to Excel. It's a much better and cleaner way of working with it. So there'll be a Windows, I think, 10 eventually. They're still working on it and trying to find out what that's going to look like. But right now, we found that having the ability to send everything to Excel is actually a lot neater and cleaner than having a separate software like that. Then we have the lab space in Germany. If you have colleagues or a facility over there, or you want to go yourself, feel free to let us know. We can set up a lab tour or even a trial for you if you want to run product over there. And then we have the same in Wallingford. A lot more equipment in there right now. So we're actually just having some new machines sent up last week. And it's going to include the new CB3 Evo. We have a new AE. We have a new SL machine, but we got all the nice attachments. So here's some of the new machines that are up in Wallingford, as well as a new CB3 Evo. And we have also a VL unit coming as well, which is the vacuum unit, standalone vacuum unit. So the lab in Wallingford is an excellent place for you to come and visit, to do trials, to evaluate our equipment, to make good choices if you want to buy new machines for not only your lab, but also for your manufacturing environment, because we can really upscale almost at a ratio of 1-to-1. So we can show you what works in the lab and how does it translate to your manufacturing environment. A big advantage of working with us is also that our colleagues from Big Additives are absolute experts on the formulation side. So when we have customers come in for trials, we actually always have access and support of our colleagues from the chemistry side to really help us ensure that the trials run smoothly, but also that they look at if there might be an alternative additive or something that might make the product better. And then we can evaluate the results. We have a particle size analyzer, we have viscometers, we have color measurement instruments, so we got rheometers, anything we need to really point out the results and show you this is how well the dispersion process worked out, and that's what it's going to do for you and your material. So with that, I'm sorry I was 3 minutes over, but I hope you forgive me and turning it back to John.
No, that's close enough for me. Thanks, Andy. Good stuff. Good stuff as always. If you have any questions, comments, need Andy to go into something a little more in depth, just drop a line in the chat and we'll get to it. A couple things here, Andy, if you don't mind, regarding, let's see, can you talk about a nanoparticle dispersion at both the lab and the production processes?
Sure. So for a nano, okay, nano is always depending on what size we're talking here, right? Particle size up to 500 nanometers, we can easily process with the basket mill or immersion mill, our TML. We can do that in our lab. We can get that done in production, and we are able to do that with pretty much standard media size of about 1 to 1.2 in most cases. Sometimes, I apologize, not sure what happened here, but we would use a basket mill, and then basically allowing us to get down to the particle size using standard media. In some cases, we may have to change out the screen and use smaller media to get there, depending on the product. If we go below 500 nanometers, then we really need to use a horizontal media mill. It's really our only way to get there. That would be with a rotor, and probably you need a high quality ceramic rotor. We have zirconium oxide, white, and then also high quality beads, and then change the screen on the nanomill after so often by when you reduce the particle size to get to the smallest particle size, like 50 nanometers and below. You really need to use super fine media. It's going to take you quite a long time to get there, but it's definitely possible. And we, with our equipment, can do it in the lab as well as in manufacturing.
Nice. How did these units compare to 3-roll mills?
I mean, the milling. I mean, it's a totally different setup, right? So a 3-roll mill is basically an old, more antiquated piece of equipment that people used to mill down their pigment, their dispersions, or products. With that was also the danger of using this type of equipment. Processing times were usually really long. I mean, I can tell you, we had a customer come into our lab, I think it was last year, and they had a product, actually it was two materials, where they were milling or using a 3-roll mill. It was a yellow and a magenta. And they came to the lab and they were like interested in the TML basket mill, just to improve the efficiency and make the process more safe. And what they found was that it took them 14 hours to mill with the 3-roll mill one of these products, and I think the other one was 12 to, I don't remember exactly, but it was about 12 or maybe even 16 hours. It was a very long time that they needed to run this material through that mill. So they came to the lab, and we ran the basket mill TML1, I remember, and we were done with one product in about 1 hour and 15 minutes, and the other material took us an hour and a half. I mean, they couldn't believe it. They were ready. I mean, they were leaving that afternoon, and they had allocated 3 days in the lab. They were there for maybe half a day. So it's a
awesome.
huge. I'm not saying that would be possible with every product. That's just what we found with most of the products that we've been running on the basketball when we compared it to 3-roll mills. So if you have a situation where you are still using a 3-roll mill and you want to explore the possibility of using or evaluating a basket mill, give us a shout, and we'll be able to make some time for you and just show you the difference, and then you make up your own mind as well what's better for you.
And having the lab in Connecticut too is just an excellent way to kind of kick the tires and test out your specific materials and see what the equipment can do. And like Andy said, our sister company, we're on their facility, so there's chemists and everything we need there. Another question here. Have you tried using your mills on pallets of biopolymers like PLA, PHA, or PBSA?
To be perfectly honest, I'm not sure.
Okay.
Reach out to us. Maybe we can do a lab trial. I would like to talk to you more in detail. I'm not a chemist by trade, so I can speak for these particular materials. And before I lead you down the wrong path, I want to know more about them. But I think most products we can effectively mill. So I don't think that should be an issue.
Okay. Yeah, I'll get you their registration details, and we'll reach out to you directly there to get that question answered, or to run some tests. We can do that. We have a couple minutes left. Is there an upper temperature limit during milling?
That depends really on the material. We like to stay ideally, I mean, that's how I set up our mill, about 50 C, 60 C, anywhere in between those two is where I want to be when I'm milling. Anything more than that, I'm already worried with solvents, especially, depending on the flash point of the material. We always need to look at that. That might actually be lower, but cooling is very important. But usually I try to be within 50 to 60 C. If we nano mill, we're putting in even more energy. We have a lot more beads. There's a lot of energy that we're putting into a mill base. So we see that it's very easy to get the temperature up very rapidly. So it's really important to have a very, very good quality, high-powered cooling system that actually at least matches the power output of the disperser or the mill. So that's just a follow-up to that is when people go and select and buy, cooling equipment, the question always come up, well, what type of chiller should we buy? Always look at the maximum power output of the motor, of the disperser, or the mill that you're using. And that should match, on the low end, that should match the chiller. You can always have more chilling power. It's always better to have more than less, but you should always have at least equal to the output of the disperser or the mill, or your product will heat up over time.
Got it. Thank you for that. I think we have time for one more. Lab to bulk upscaling. How do you better correlate lab and production mixing times?
So again, there is a couple things we look at. First of all, you want obviously diameter blade to vessel ratio, fill rate. You want to absolutely look at tip speed, more important than anything else, really, like RPM or anything that because you're going to run much faster in the lab than you ever will in production. So RPMs really don't mean much. What means most is the tape speed should be the same. The blade geometry should be the same. Again, cooling should be the same. So we have fill rate the same. You maximize all those things. Then you should have a very good way of upscaling from the lab to the manufacturing plant. But tape speed and blade diameter, vessel ratios are very, very important.
Nice. Okay. Well, I think that wraps it up. Good hour there, Andy. Thank you for your insight and expertise as always. Check out if you're interested in joining us for the part 2, the media milling. The link is in the chat. You can register. Additionally, you'll receive an invite that's scheduled to go out this Friday. But the presentation is next week, Tuesday, same time, same day as this one. Also, once you get that recording, if you have any other questions, you can simply hit reply. It'll come to my team and we'll route that to Andy or someone on his team in your area. So with that, thanks for joining us. And I'm sure we'll see some of you next week at the media milling part of this. Andy, thank you.
Thank you.
Always. And everyone have a great rest of your afternoon. We appreciate you.
See you guys next week. Make sure you register. We have a lot to talk about, so please come back.
Take care, everyone. Thank you.
Bye.